Welcome to the Acids and Bases, Chapter 14, Section 3, narrated presentation. This is Part 2. Part 1 covered the remainder of the first two sections, which included all three theories of the, I guess, acids and bases, which would have been the Arrhenius, Brønsted-Lowry, and Lewis theories. Let's get to it. Okay, there are approximately 17 slides, and this is number 2. Of course, we're not really doing a student learning map, but this is a very good question that might just show up on the Chapter 14-15 combined unit assessment here in just a couple of days. Here would be the last section lesson question if you want to review that. You should be able to answer it when you're done reading and when you're done taking notes and when you're done watching this presentation. Anyway, so it's a good question. Here we go. Okay, in section 3, what do we have here? The objectives, nothing noted that's different, so this comes right out of your book. Describe what a conjugate acid is, a conjugate base, and what amphoteric is as far as compounds. We would like to also explain the neutralization reaction and explain just a little bit environmentally about how acid rain damages structures, primarily marble, but it damages everything. Many things, not everything. Okay, running into the content. So Brønsted, so Ba at the very top, Ba and Bb. Brønsted acids and Brønsted base reactions are equilibrium systems. Here, and I think I have my pen activated, so I think I can write on this thing. There we go, and here we are. Okay, thank you for your patience. All right, so this first bullet here. Here the Ba, the Brønsted-Lowry acid, just Brønsted acid for short to make it convenient. The Brønsted acid will lose a proton to the Brønsted base, creating ions as products. The Brønsted base that accepts the proton is then, as a product, in position to lose the proton it just gained. So the Brønsted base can actually function as an acid because it has that extra proton. Consider water. Okay, think about water that has gained a proton. Well, it would form hydronium. This would be correct. Well, notice the hydronium, of course, now has an extra proton. It's in a position to lose that proton and go back to water, which would be neutral, a neutral compound. Well, therefore, then the hydronium, which has this extra proton, can now function as an acid. And that's all that means. Okay, third bullet. The Brønsted acid that lost the proton could, as a product, then actually reaccept a proton and then function as a base. So wherever this proton came from in my example, okay, so whatever this is, let's say it was HCl. That meant that this would have been a chlorine ion. So this is all just kind of separate over here. That chlorine ion is in a position to reaccept the proton, so which would lead to this thing over here. And so if it did, well, that means that the chlorine then can actually function as a base when it becomes a product. This Brønsted acid, Brønsted base reaction is a system in equilibrium. Now, I chose probably an incorrect example because HCl reacting with water will exclusively form hydronium and chlorine up here, and they will not react in the fashion we were talking about a moment ago as an example. However, a weak acid like acetic acid, HCH3COO, combining with water, is a reversible reaction to make the H3O and the CH3COO ion. This is a system that will attain equilibrium because most of your reactants will stay in molecular form. They do not react very well. You will have only a slight amount of product, and that slight amount of product can react and form the reactants again. So therefore, this system, which you have a Brønsted acid and a Brønsted base, and then this thing functioning as an acid as a product, and this functioning as a base as a product, according to the Brønsted theory, then will exist in equilibrium. And that's kind of neat. I like that. Things have multiple chemical functions. Okay, moving on. Conjugate acids and conjugate bases. So this leads into the fact of when they become products, do we continue to call them acids and bases? Because then all of a sudden it seems like, everything's either an acid or a base in these types of reactions. And how do you keep track of all that? Because remember, chemists, kind of like physicists, chemists are accountants. We need to count for everything. Where is it at? Nothing disappears, the whole law of conservation of mass thing. So with that, we need a good labeling system in order to keep track of all this. And so what they have done is they have used the term conjugate. So when we look at, let me get my pen going here. So when we have a conjugate base, defined the species that remains after the Bronsted acid has given up its proton. So in this reaction here, HF, hydrogen fluoride or hydrofluoric acid, will donate the proton. So this clearly is the Bronsted acid. It will donate the proton. Water clearly will accept the acid, so that will be your Bronsted base. That's where the hydrogen will go. That will form the hydronium ion. Well, what's left? After the HF has donated the H, well, what's left? That's your fluorine. That fluorine is now called a conjugate base because it could reaccept the proton. The hydronium is now called a conjugate acid because it's in a position to lose its extra proton. So this is how we differentiate the true acids over here as reactants from the created acids and bases as products. And typically the created acids and bases in conjugate form are almost always weaker. There are cases when you can kind of reverse that and create stronger ones, but that is less likely. Okay, well, we've already mentioned conjugate acid, so let's talk about conjugate acid. It's the species that forms from a Bronsted base that's gained a proton. So whatever gained the proton and is now a product, we simply call a conjugate base. It's the same example down here with the hydrofluoric acid in the water. And so we've already identified the hydronium as the conjugate acid. Now I do have to mention one thing to you, and that is on this slide. Typically in any textbook I have ever run into, and here I have the typical terms over here, that most textbooks, most websites are calling these things conjugate acids and conjugate bases. However, your textbook, your authors developed their own system, very much like when we were naming and formula writing. And I used a system that was created by an author named Stephen Zumdahl to call the compounds like type 1, 2, 3, and 4. Now we haven't used that much, of course, because we know what the compounds actually are. But it was a convenient way to teach it, to group it in order to learn the system. Well, some authors do that. Sometimes it catches on, sometimes it doesn't. Well, the type 1, 2, 3, 4 is unique to Stephen Zumdahl. I haven't seen anybody else use it, and it doesn't appear in college textbooks to my knowledge. Likewise, in your textbook here, they, instead of using the term conjugates, although it's mentioned in your textbook, they actually are giving kind of like a numbering system. And so you see that down here. Let me get the pen going again. So here in our text, what they're going to say is that the Bronsted acid, they're going to call acid 1. The Bronsted acid always then creates the conjugate base they call base 1. So acid 1, base 1 is the pair that goes together. Water functioning as the Bronsted base, they call base 2 instead in this circumstance. And base 2 will create acid 2, which we would have called the conjugate acid. And so here again, the numbers match up. Base 2 to acid 2, acid 1 to base 1. That's how they pair that up as opposed to conjugates. However, like I said, it's unique to your textbook, unique to your authors, and they haven't over several editions modified it. So apparently teachers like me don't complain loud enough. Okay, let's move on. What about strength of acids and bases? We understand about strength of acids and bases. However, what about these conjugates? So let's take a look at the first example. Here we have strong acids, and strong acids will create weak conjugate bases. And so here we have a strong acid in hydrochloric. Hydrochloric really ionizes practically 100%. Therefore, almost all the products, pretty much 100% of these products, will remain as a chloride ion and a hydronium ion. They do not re-react together, because of the solvated particles of water isolating the chlorine, and the fact that the hydronium actually has a much tighter hold on that hydrogen ion than chlorine can to pull it back. So for a variety of reasons, we start with strong and over here, and we end with weak over here, very weak. The stronger you start out with, the weaker you end up with. So it's very much like a teeter-totter, like a seesaw, if you will, as far as a visual. Well, weaker acids can create stronger conjugate bases. So now let's consider acetic acid. This is acetic acid. Sometimes the hydrogen right here is written in front, and sometimes it's written in back. Normally in organic chemistry, it is actually written here because of the COOH or the OH grouping, because it's a carboxyl group or a hydroxyl group, depending on how you look at it, and that's the acidic part of that molecule. Well, in this case, it's a weak acid, and it is reacting with water, which is a weak base, and when they actually react and they create the acetate ion and the hydronium ion, it turns out that these are fairly reactive, and so when they form, they will re-react pretty readily and make the reactants again. So this is why mostly, it's like maybe 99, I'm going to make up a number here, but mostly 99% in a solution will be your molecule of hydrogen acetate and your molecule of water, and very little, your like 1%, will be these ionized acetate and hydroniums. Because they are so reactive, because they are so strong, they are able to re-react. So strong makes weak, weak makes strong. You can read down through here as far as the explanation behind that. I will move on. Okay, so table 6. There is actually a table in your textbook in chapter 14, table 6, where it lists Bronsted acid and Bronsted base strength, and it compares their strengths with their conjugates. So for instance, a very strong acid right here, which would be perchloric, it's in the top 7 strongest acids that are available to chemists. That perchloric acid will actually create a chlorate polyatomic ion when it loses its proton. This is very strong and this is very weak, so that's exactly how that works. Whereas a weak acid, such as carbonic, will create a stronger base, which is your hydrogen carbonate ion. When it loses one of these protons, what remains actually is a stronger base that can more easily re-attract a proton than it will actually to lose the second proton, the second hydrogen. Weaker acids can lead to even stronger bases. So here we have this particular hydrogen carbonate ion, which up here is a base, down here is actually now functioning as an acid if it indeed loses the hydrogen. And when it does, this is even stronger because the carbonate polyatomic ion is very competitive to take back up a hydrogen proton as opposed to remaining just carbonate. And so that reaction is very likely to happen to where it will collide with something to steal that proton back and go back to the hydrogen carbonate polyatomic ion, which then can still re-react and form the hydrogen carbonate molecule because it's a weak acid anyway. And so you have very small ionization percentage. So that's how that works. Here's that table, and that table, you can read this. I don't know what page it's on in your textbook, but it should be easy to find. So it starts up here with, let me change the color of my pen. I think that's not going to show up so well. So it starts up here with hydriodic acid, HI, perchloric acid. What you'll notice is all of these right down through here are very, very strong acids. This is kind of like the hit list of very strong acids. And the stronger these acids are, over on the other side, these are the conjugate bases. What happens when the proton is gone? Well, this is what's left. When this is what is left, these are then as strong as the acids are, these are equally as weak. And so it's very, very systematic, and I believe it makes sense. Otherwise, this list actually has a lot of things going all the way down to the weakest, like down here. This is the weakest of acids, a hydrogen molecule, and this would be the strongest of conjugate bases, which would be the hydride ion, a hydrogen that's actually gained an electron as opposed to being just a proton, being an ion. And so, and this thing all matches up. Of note, where is it here? Ammonia is here and here. So ammonia can function as both an acid and a base, and water is here, and water is here. Water can also function as an acid or base. There are a few other things on this list, but interesting that we have some chemicals that are twice because of their ability to be what is called amphoteric. It'll be a term we'll talk about later. The ability to behave as either an acid or a base depending on the situation chemically. Well, here we are with amphoteric substances. Any species that can react as either an acid or a base. So in the first example, we have sulfuric acid. Let me swap out the pen color. We have sulfuric acid combining with water. Sulfuric acid clearly loses the proton, so this is our acid. Water then accepts the proton. This is clearly our base, and that would be a Bronsted acid, and this would be a Bronsted base. If we want to extend this, by the way, we now have a conjugate acid, and we now have a conjugate base. Down here, we have ammonia and we have water. Well, let's see what happened in this reaction. We have ammonium, NH4 positive, so therefore the ammonia accepted a proton, so the ammonia is functioning as a Bronsted base. Where did that proton come from? It came from water, now functioning as an acid, because look what's left over. A hydroxide. Well, if you lose a hydrogen from, or a proton rather, from water, what you're left with is a hydroxide. And so therefore water functioned as an acid. Base up here, acid down there. This is amphoteric. Ammonia can actually, so this compound right here actually can do that as well. Many can. So here water functions as either an acid or a base depending on what it's reacting with. Other examples, any conjugate bases of polyprotic acids, such as from carbonic acid, if you have the hydrogen carbonate ion because a proton was already lost, well, that can either lose or gain. Likewise with sulfuric acid, after it's lost a proton, you have hydrogen sulfate, the polyatomic ion. That can either lose or gain. And then we have the dihydrogen phosphate, or if you lose another proton, the monohydrogen phosphate. All of those coming from phosphoric acid, and those would be able to either lose or gain protons accordingly. Oops. This is just a mention of that hydroxyl group from the actual carboxyl group, if you will, for organic acids. So this down here being a carboxyl group, and that portion of it being the hydroxyl portion of it. So any species with a hydroxyl group is acidic when water can attract the proton from it. The more polar the bond, the easier the proton is lost. Consider hypochlorous acid all the way through perchloric acid. The more oxygens, because oxygen is very electronegative, the more acidic the substance, the easier it is to lose this particular proton. Now the structure would be that the hydrogen is not bonded to the chlorine, even though that's the way it's written. It's bonded to the oxygen, and these oxygens are bonded to the chlorine. And the stronger this bond is, the weaker this bond is. And the more oxygens, the weaker this bond actually gets, and the more easily the hydrogen is lost. And so that's why acid strength goes up with more oxygens. The more neutral the compound, the more likely it will be basic. So acetic acid, ethanol, acetic acid slightly acidic, ethanol slightly basic. Neutralization. So here, SA just stands for strong acid, SB strong base. If we have a strong acid reacting with a strong base, when they react, they will make a chemical salt and water. If we are dealing with inorganic acids, which is primarily what we have dealt with in our class is primarily an inorganic chemistry class with a little organic on the side, just for flavor, just for a little bit of something, right? Okay, so what do we have here? Well, in our example, so I can, here's my pen. So here I have a strong acid. This strong acid actually is HCl, but I'm showing it ionized because that's exactly how it should appear in a solution. Here I am reacting it with sodium hydroxide. So N, oh, that's horrible. Sorry about that. Let's try that again. NaOH. I can't say I love this pen, by the way. This is to write on these slides like this. Oh, forget about it, right? Okay, so here we have a very strong acid and a very strong base. They are in the top 10 of strong acids and bases from the first presentation, actually. Well, when they react, they will neutralize each other, and they will create, of course, water and a chemical salt. In this case, I chose the easy one, sodium chloride. But remember, there are many chemical salts out there. Sodium chloride is simply one example of many. The reaction of hydronium ions and hydroxide ions to produce water is the neutralization part of the reaction, which also indicates that pH, which is a numerical measure of the acidity or basicity of a substance, approaches or equals 7. Because it's a 0 to 14 scale, 7 is dead on in the middle. It's neither acidic nor is it basic. So water is a 7, pure water. In this case, this is exactly the same example again, simply reiterating that. And then the net ionic equation. Okay, so think about what you're going to delete here. So if we lose the chlorine, which is a spectator ion, the sodium, which is a spectator ion, then over here and over there, what's left? Hydronium combining with hydroxide, making water. So that becomes our net ionic equation. Any acid-base reaction that results with a net ionic equation creating water is a true neutralization reaction. Okay, I flipped too many slides, so I had to go back and re-record a couple of things. So hopefully it all connects back together. This particular slide simply just talking about acid rain, which is certainly a very bad environmental problem. And the problem stems from the fact that with industrial pollution, we are sending, very much like volcanoes will do naturally, but on typically on a smaller scale, because volcanoes are often short-lived, even if it's a 50-year span of time. In the scope of things, that's short-lived for the globe. But industry, once it kicks up, it keeps going, and so we're just constantly polluting the air. And we're sending many gases like nitrogen monoxide, nitrogen dioxide, carbon dioxide, sulfur dioxide, sulfur trioxide, and others. And all of these gases can go up, and just like on a sheet on a homework assignment, if you take these gases and bubble them through water, you start to make acids. And in some cases, you start to make some of the very top 7 strongest acids. Well, the same thing can happen in the atmosphere. The atmosphere becomes the test tube, and we have rain droplets. Even on a small scale, microscopic scale, rain droplets become test tubes. And so what happens? Well, we make acids. And not only do we make acids, we make some strong acids that come down in raindrops, and then they react with plants, they make soil, and they make groundwater and storage water like ponds, rivers, lakes. They can make all of this way more acidic than it was ever designed to be for the life forms that are actually existing in that water or in that soil. So let's consider down here, we have sulfur trioxide is a gas reacting with water, and this would be in the atmosphere. So this is like if I can do this, it's a raindrop. So when we react it together, what do we make? Holy smokes, that sulfuric acid, that has like a pH of almost 0. This is nasty stuff. And when that happens, of course, it comes down as far as a raindrop. In that raindrop, not only would you have maybe just a touch of the molecule itself, but it's going to ionize, and it's going to make your hydronium, your hydrogen sulfate, and your sulfate polyatomic ions, all of which are very reactive and can interact with the environment, and never in a very good way. Okay, now check this out down here. Here we have calcium carbonate. Calcium carbonate we can call marble. There are a lot of compounds that are made out of calcium carbonate. Also, it's limestone. and other things besides eggshells actually are made of it. But of course, we're not talking eggshells really at the moment. We're talking marble or limestone. Well, if you have a marble statue that has been sculpted by Michelangelo, it's sitting outside of a church somewhere over in Europe, and what happens? Well, it gets rained on, and if that rain contains a significant amount of hydronium ions, that raindrop is acidic, just like the quadrillion that fell with it and hit the marble statue. Well, it breaks the statue down by reacting it, creating calcium ions, carbon dioxide, which actually bubbles away. If you actually looked at the raindrop on the calcium or on the marble, you actually may see bubbles in that raindrop if it's acidic enough. That would be scary, wouldn't it? And of course, water, which really doesn't do anything, doesn't harm the environment. But the point is, this isn't marble. This is not marble. And if this happens long enough, then the marble actually gets chewed away, gets eaten away, chemically reacts away. And so that really wonderful statue now just kind of looks like a blob of rock with a vaguely, human or horse shape or whatever it was. And certainly it was not what was created a long time ago. And it's because of accelerated weathering, chemical weathering, because of the Industrial Revolution and our lack of control of air pollutants. So real bad problem, and it's global. However, it's regional because of weather patterns that not all areas experience the same type of environmental concerns, even though all of this is in the environment. All right, I believe we are just darn close. So let's see where this goes. So problems to consider, because this is pretty much the end of this particular chapter, although we will be combining section chapter 15 in with chapter 14, but you might want to consider reviewing a few of the problems out of the book. Take a look at some of those. Can you answer some of these questions? Most of this looks like actually all of this is coming out of the chapter review at the very end of the chapter. None of it's assigned other than you should look at it, and if you understand acids and bases from the point of view of this chapter in the context of the presentations, you should be able to generally answer these questions with confidence. Let's see where this goes. End of chapter 14. Proceed on to chapter 15 with the same. Of course, we're not doing a student learning map, but we are going to proceed on to chapter 15, not in this presentation, but in, I believe, 2 others, maybe 3. I haven't created them all fully yet, but I may need it. So what is in chapter 15? Well, chapter 15, we want to look at the concept of pH. We want to understand a concept not as many people know of pOH, which one looks at the acidity of something, one looks at the basicity of something, but they actually all work together. And we can then develop the 0 to 14 scale. To do pH, it's actually a mathematical formula, which is the log of the hydronium ion concentration, which gives us pH, or the log of the hydroxide ion concentration equals the pOH. And out of all of this, we get these numbers 0 to 14. The closer you are to 0, the more acidic you are. The closer to 14, the more basic you are. And if you're 7 on in the middle, you are neutral, like water. So we want to develop that. We also want to develop a constant value called Kw, which is an ionization constant. Ionization. Talking right at the same time, Spence. So it's an ionization constant. We'll develop that as well, even earlier than this material. And then we will actually go into, in 15.2, we'll actually go into a skill called titrations, which is a really neat lab skill, and I wish we were together because it'd be a really cool lab to do. However, you can look titrations up when we get to it, and I'll try and find some videos that show some pretty good titrations. But the idea is you mix an unknown concentration, so I'll just use square brackets for concentration, with something that is known concentration. So this might be a base, this may be an acid, and based on the ratio of how they interact together, and we can use an indicator that'll change color to tell us when a reaction has occurred, so it can be very visual, or we could use probes and we could watch for concentration spikes and all kinds of really cool computer-based indicators. that when this reaction occurs, we can actually then run these values of how much unknown did you use, how much known did you use, what was the concentration of the known, and run it through our old friend stoichiometry, and then find the unknown and make it a known concentration. And you can always also use titrations for known concentrations to verify, do I really know this concentration? Is this concentration really a 4.7 molar hydrochloric acid solution? We can actually test that against like an uber known, something that is absolutely 100% known. Most of those types of known solutions, which are called standards, are actually created by chemical companies that where they have amazing equipment that can really verify that to 5 decimal places this thing is exactly 10 molar, and so we can use that and use it with confidence to then verify what we have in our labs where we're making up chemicals where we don't have all of that fancy $1 million equipment in order to do it. So this is where this chapter goes, and I believe the next is just the unit essential question leading us into chapter 15. And then the very first chapter 15 lesson question. We're again not doing student learning map, but that's a good indicator for me that, hey, wrap it up, Spence, we're done. Okay, well, I will see you, hear you, or you'll hear me rather, in the chapter 15, section 1, part 1 of the continuing saga of acids and bases. So be there. Thank you.